So let's dive in and see what we have for today. Good. So
I usually tell one of my friends, Ima. I usually tell him that it's as if you have seen into the future since 2020, because most of the things you told me 2021 are really happening. They are playing out on daily basis. They keep on unfolding on daily basis now.
and John, it's always like that. That's why some of us we don't really like. I tell my wife I permanently live my life on the future dimensional plane,
Mm, mm,
because
mm,
the the present is already with us. The past is gone. The future is
mm.
unknown. So
So none.
if you don't continuously try to live in the future, I naturally as a person, for me, I try to be 10 years ahead of my colleagues.
Mm.
So when other people are in 2025, I'm already trying to think of what is going to happen in 2030.
Yeah,
And so
and
I permanently live on the future dimensional plane.
mm,
I
mm,
remember there was something that happened once, I think it was last year. We were talking with my wife, and then I started asking her when is I told her her passport is going to expire this year, right? In 2025. And then she got angry that what she's telling me is different from what me I was talking. I said, because I'm already thinking about it. And she got very angry, like, wow, like I because I don't want things to catch me by surprise.
mm,
I don't like life happening to me, like so I permanently, for example, if I have a conference in London, I will I will already pull out the map of that location. I'll study the place, how the building looks. So,
mm,
I'll check all the environment before I even go there. So when I get to that location, I won't be confused. I'll be able to
mm.
figure out. Yeah, so I just keep doing that. Like before my PhD finished, I already got a postdoc. I had like six, I think maybe three of no, like 4 5 months. No, let me say 3 months or 4 months remaining to my PhD when I left Italy.
Mm,
I didn't wait to finish PhD, then I'll start looking for what to do next. No, I
mm,
started looking for what to do next when my PhD was even like in my second year. I started doing interview with different places. I
mm,
don't I don't just sit down. I plan ahead, because if you don't, you get trapped in the cycles of life. Life is not
mm.
the way you put it. It's not a straight line. So
It's true.
if you want to understand all the gradient descent of life, you must be able to get yourself going so you don't get trapped in the local minimum.
True.
Do you understand? Anyway, um, let's start. So I don't know if you could see my screen.
Yes, I can see it. But
Okay,
boss,
great. Yeah.
there's something I want to do. I want to
Mm.
be, I don't know, I want to be seeing the screen and also use the system to be on the Jupyter page. But then if I click that page,
Oh,
I
okay.
don't
What
if you
you
can't
need? No,
see the
no.
same
What you
browser.
need to do? Okay, this is what you need to do.
Okay.
Can you see this button here for maximize and minimize?
Yes, yes, yes.
Okay, if you clicked this, you see it will maximize. If you clicked this, it's a kind of, so what you do, you come and shrink it. Look at it. You come like
Okay,
this,
okay.
reduce it,
Okay.
Go up again. Reduce it very well to what you want. Reduce it
Okay.
again. And then now, if I open, for example, CMD for command prompt, so now you could
Okay.
so you could reduce this one like this, and then
Okay.
Jupyter Notebook. So
Okay.
now when it opens, you shrink it as well.
Okay.
Good. So this is now going to open. So the same thing, you drag it, reduce it to what you want.
Okay.
So it could be smaller. And then now you drag it up like this. So now you see you have both of the windows open. So this will be open and this is open as well. So the both of them, and if you like, you could increase it to be full screen here. Yeah, if you could like you do. So now you have the both of them. You have the uh lecture on and then the Jupyter Notebook screen. So any of the
Yes.
page you could be working on them. So try it out. Let's see if it works.
That's what I'm doing now.
Okay. Okay, so who is the okay, Olga. Olga, how are you?
Who is number?
I'm fine, sir.
Good. It's been a while. Were you in the last class?
Yeah, it's been a while. Sir?
Were you in the last class?
No, I was not in last class.
Okay. But you were able to follow
Yes,
the
sir.
video, right?
Yes.
Okay, great.
Yes.
Boss,
So
I can only drag it from the top down, but sideways the arrow is not coming up.
like if you go, you're going to see an arrow like a cross.
Yes, from the top is working. I can bring it down to the top,
so
but the side, the two sides
you can see my own. I could actually drag it. What you need to do is if you go to the side, okay, try to maybe let me see what you're doing. If you can share your screen.
Where do I share now? Okay, I think the issue is because it's the same browser I used to open the Microsoft Team. So when I'm
really?
it will be
okay. So if that's the case,
the window is they're on the same browser. So if I'm trying to minimize this one,
I got your point. So what you need to do, okay.
I should try to see if I can open it on the Microsoft Team app. Okay, no issues. Yes. I'll be using the phone. Let me use my phone and combine.
Okay, but you could also copy the local host that you see on the home of the Jupyter Notebook.
Okay.
Copy that link, then you can go to a new browser, let's say Chrome, and paste it. Let's see. No. I think that would take me to the browser one. Okay, no, don't worry. I think you need to reduce the volume. Okay, I think that won't work because it will take us to the cloud Jupyter Notebook one. So what we need to do, we have to reset it to change the default browser. So we have to like change the default browser to your browser and all that, and that could
Okay, no issues. What I think what I would do is the app, the team app is not working too fast, so I normally use the browser to open the Microsoft thing. But I think what I'll do next, I'll just work on it. I'll update the app. But let me use the phone combined with it today to save our time. Yes.
Okay, fine, good. Okay, so let me share it again, and then we could start. Good. So I hope you all can see my screen now, right?
Yes, sir.
Okay, that's great. So I'll maximize this so we could see it clearly. So last week we talked about a brief introduction to machine learning last week, where I told you guys about the supervised learning and also the unsupervised learning and a bit of the reinforcement learning. I also talk about, if I remember clearly, an example of supervised learning when I talk about the regression problem, and also I talk about the classification problem. And
Yes.
I wish I could go in very detail to talk about each of these examples of the algorithms. However, I wouldn't dive so deep inside some of them. I will leave that completely to you. You could be able to read and see how to be able to follow up on some of these things. But today we are going to do more of the practical as promised. Because I was reading something yesterday, and it got me thinking. I was reading the Bible yesterday in, I think, in First Corinthians 5 or so thereabout, and I got caught up by a word. Sorry, I have to bring the Bible here because it's very important. And it says that the kingdom of God is not in words but in power. So what I mean here is that whatsoever you do, the theory, no, you need to delve into the practicals. And something like data science, AI, it's very, very practical. When we do the practical, that's how you are going to learn. And whenever we do these things, try to practice them, run them and see, get the errors. Don't be scared to fail. Okay? When you fail, when you have errors, find a way to debug them, go back to them, go back again until you're able to solve some of the problem. So today I'm going to briefly look at these slides and then we'll dive into the practical section. So like I said, we're going to look at supervised learning, where basically we'll focus on regression, classification in Python Jupyter Notebook. So we have already talked about this in our previous video of what supervised learning means, where we said in this case, you required a sort of supervision. And the supervision here is the label that you have. Sorry, can you turn off the mute the phone there? Good. So the supervision in this case that you require, it's the label. So the label here that you require is because you need to train the algorithm on some set of features, which are in statistics, you call them the independent variables, or you could also call them the explanatory variables. You need to train the model on these explanatory variables to recognize a particular label. So, for example, each of the rows, we call them um, the the instances or the examples, and this could mean human being. They could mean so many things. They could mean products. They could mean a set of responses to a particular questionnaire, and so on and so forth. So what you need in this case is when you have these features, when you have this data set, you get a particular label that you want to get out, or an output that you need from these features. For example, I told you guys about the email spam, that when you have, if you go to your Gmail, you will see that you will see a spam where you could be able to see some messages that don't come into your inbox. That's a machine learning that was used to filter these emails because they suspected that these emails have red flags. So because of the red flags, they removed these emails because they are likely from scammers or from other people. Sorry, can you mute? So there is a noise in the background. I think Olga, can you help us to mute?
Okay, let me do that.
Okay, good. Thank you. So by the time you have these instances, you will be able to predict or make predictions. So in the supervised learning, consider it like a student that goes to a class to learn. When the student goes to the class to learn, the teacher will teach the student on different topics, on different areas. And at the end of the teaching, the teacher will evaluate what the student have learned. Now, the output in this case is going to be your grade in that particular course. Are you going to have an A or a B or a C and all that? But remember, the teacher imputed something inside you, which is the topics or the various areas that he taught you in the class. The output now is your grade. So that's how these things work in the real world. Then there are different areas of supervised learning. So we are going to talk about some of the key areas of supervised learning, which is the classification problem and the regression problem. And then we're also going to talk about the supervised learning algorithms, both in the classification world and also in the regression world. Then lastly, we're going to talk about the hand-on example on the regression and classification problems. So, like I said, the prerequisite will be for you to have installed Python. Also, you must have had a Jupyter Notebook from the previous videos. If you have not watched it, we talk about all this. So, like I said, what I talk about this supervised learning, that it is just like a teacher teaching you in a class. Now, consider a situation where you have a set of label. Now, these are futures. Remember last week I told you about the future that differentiate an orange from an apple, where we talk about the roundness, we also talk about the colors. So the same way, for example, we have this set of futures and we want to label them. We want to train the machine to recognize, is this going to be a carrot, a tomato, a bell pepper, or it's going to be an orange, for example. So for what you need to do is to feed the training in the training algorithms, you need to feed it with all the features or characteristic of each of these labels. So you need to show the machine what it means to be a tomato, what it means to be a carrot, and what it means to be a bell pepper. So by the time you show the machine you train it on all these characteristics. So just like the classroom where the teacher teach you on all these various topics, the next thing you need to do is to make predictions. So that you're now going to hold a portion from the data set, let's say maybe 10% or 20% or 5%, depending on how the case may be. But the most popular case is 20%. So most times you hold that portion away from the machine when you're making prediction and give the machine only the futures and tell it and say, okay, now I have trained you, I've shown you what futures differentiate a tomato, a carrot, and a bell pepper. Now, here is this futures. Tell me if it's going to be a pepper, a carrot, or a tomato. So that's what you do. So you have to have the futures, you have to have the label. And these futures can be stored in a database or even a data lake or some cloud infrastructure like the AWS. So by the time you have all these features stored somewhere in the database, you can easily retrieve them using, for example, SQL, and then you could save them in a machine readable formats like CSV files or HTML or XMLs, depend on the kind of thing you're working with. So, like I said, consider yourself in the class and then the teacher teach you. After he teach you, he evaluates your learning. So that's what supervised learning is all about. So it is that branch of artificial intelligence that focuses on training the models in order to make predictions or decisions based on labeled training data. So the goal in supervised learning is for us to make predictions. So irrespective of the type of supervised learning tasks you have, be it a regression task or be it a classification task, the goal is for you to be able to make prediction. The goal is for you to be able to understand what this machine is doing in the first place. So in the case of regression, so there are two main types of supervised learning, the regression problem and the classification problem. So in the case of regression, the outcome and even most of the features are continuous. Not in all cases. There are cases where we could have a binary, but note at the back of your mind that in regression problem, we are dealing with continuous values. And I told you a brief about continuous values. I told you that continuous values are those values that you find them closed in the number line. It means these are values that are in decimals. In real life, a height is a continuous variable. A weight is a continuous variable. A BMI score is a continuous variable. Stock market prediction or stock exchange stuff and all that, if these are continuous problems, the reason is because you cannot be able to hold them down in the in the particular fixed position. So they are not a whole numbers. They are things that you could approximate them. They are things that you could easily follow their tracks over time, or not time series in all instances or cases, but these are always things that are continuous on the spectrum. So a good example is the housing price problem, where you want to determine the price of the house. Now, the price of the house could be determined by several factors, and I highlighted that in the previous video. So if you haven't watched that, you could take a look and get to understand what that means. So classification problem, on the other hand, you are dealing with categories. And when we talk about categories, there are several kind of categorical variables. It could be nominal, it could be ordinals, it could be orders, but most of the time when it's nominal, it's just normal categories. And when it's ordinals, it means that it has to be do with ranking. For example, when you are dealing with security forces like the army, you have to know that ranking is very important when you are going to consider things. For example, there is going to be a difference between a private, a sergeant, a warrant officer, and so on and so forth until you get to a general. So these are examples of categorical problems. So like I talked about the email spam. So if the email is going to be a spam or non-spam, it's still a classification problem. And you see that very common in your Gmail accounts. When you open your Gmail inbox, you will see that there is a spam message that do not come to your normal email message. And the reason is because these ones help you so that you can be not get easily frauded, because there are so many fraudsters that try to use these approaches to bring people into their web. Then there are other examples like in medical health, like the case of cancer. You want to know if it's going to be benign or it's going to be normal cells. So if it's not cancer, if it's not cancerous, then you said it's a normal cell. It's not, and then if it's cancer and all that. So there are several features that you could use to be able to determine that. For example, you have to use features from, let's say, CT scans. You have to use features from even looking at some of the measurement that was taken from the lab test to be able to arrive at that conclusion. Now, there are several other classification problems. Then I want to make these notes before we move on to the next slide. Now, classification problem could be binary and it could be multi-class. Just like the regression problem can also be simple linear least square regression, or it could be multiple regression problem. So when we are talking about simple or multiple regression problem, just know that we are talking about the response variable in this case. When we now have several response variables that we are looking at simultaneously, it becomes a multiple regression problem. But when we have just one response variable we are looking at a time, it's a simple regression problem. The same thing in the case of the classification problem. When we have just two outcomes that we want, if it's, for example, a cancer or it's not a cancer, then it's a binary problem. But when we begin to have several other things, futures beginning to come into play. For example, we want to know if it's going to be a cat, if it's going to be a dog, or if it's going to be a horse. That's a three-race problem. So that's not a binary problem. Rather, that's a multi-class problem. So again, you have to also understand that the more you have the response, the more the dimension increases. So it means you're moving away from the two-dimensional plane. Okay, so let's move on. So what are the common supervised learning algorithms that we have? There are several of them, but you have to start. You know, when you want to build a house, you have to build it from the foundation and then you go up. The same thing in learning AI. You have to start from the grassroots. You start from the little ones and until you build until you get to that extent. So in the case of the regression algorithms, we have, for example, linear regression problem. So there is the linear regression algorithms that attends to things like simple least square problems. We also have the decision tree classification. Then we have the random forest classifiers. So when we talk about regression, if you are a math student, not necessarily a math student, even an economics or it's a kind of a very popular equation. We see it all around us. So the regression problems that with the y equal to b, which are the coefficients of regression, where we talk about these ones to be the slope and the constants. So and then we also have the error term. And then we begin to come out to begin to look at some of the properties of linear regressions or the assumptions of the linear regression. So what we mean here is that you have this set of observed variables, or we call them futures. So this could be x1, x2, x3, x2, and these x's can be different futures. So like I emphasized earlier on that these futures could come in different handy. It could be talking of weight, BMI, talking of in the case of you could also look at things like salary, location. So it could be anything. So at the end of the day, what do you want to measure these futures to understand? What sort of outcome you want to use these futures for? So there is the independent futures. And then we have the dependent futures. And truly, of a truth, you could see these futures depend on it because the fact that these values here could go up or come down depend on the futures we put in here. So the more you load these futures, it could determine how this value could go up or come down. So the next thing we need to do is to capture the variability that happens. So when you have these futures, you try to put them on the XY plane. So when you put them on the XY plane, the reason is because you see, I always want you to understand that everything reduces to try to put a representation, build this whole sort of artificial planes where you could easily represent objects in order for you to understand the variabilities that are happening. So that's what we are trying to do when we try to put these things on the XY planes. So when you put them, remember these are set of measurement that you measured in the labs or you took from the field and so on and so forth. So you expect some sort of random errors to happen. The reason of these random errors is that we always understand that these values are not always precise. So there is always going to be that room for these errors to happen. But that's a story for another day. And we expect someone in the lab to always make sure that these errors are minimized. Is it going to be a type 1 or type 2 kind of errors and so on and so forth? So we always going to have the error time, which is like the variability of how these things occur. Then we have the intercept, which is going to be then we have the slope as well. So all this put together, remember your normal y is equal to x plus c from the normal linear equation. So it's the same thing. So consider this b1 x1 beta 1 xi, yes, plus this to be that y equal to mx plus c. And then you know, I remember if you want to start what do we call it, differentiation, you know, you have to come from this slope stuff, and then you begin to try to have the different kind of the slope where you have y equal to mx plus c, where you have y equal to mx alone, and then you now substitute these things to differentiate, and then you begin to come, then it takes you to the first law of differentiation. Then you move to the second law. Then you move and move and move and move and move like that. Then by the time you understand differentiation, you move to integration and all that and all that. So this all lies on the dimensional planes. So we, in the simple regression problem, like I told you, we just have this y equal to beta naught plus beta 1 x1. And this could be you know, a very simple thing. But the moment you begin to add other variables, it becomes multiple. So now you could have y equal to beta naught plus beta 1 x1 plus beta 2 x2, and so on and so forth. So the more you add these variables, the more complex the system becomes. But in the case of decision tree, however, it is a different approach that it's using, called the rule-based method. So the rule-based method here is looking at what we call entropy. So the entropy is basically what, you know, the degree of randomness. Okay, so what it looks is that if this entropy is to some certain extent greater than a particular threshold, it splits the decision. It becomes yes or no, and then like that. So we always going to have the first one, which is acting as the root. So the one with the highest value will take the one that, or the most dominant feature will likely be the root. So that, when you now looked at it, what now determine if how the splitting goes. And for example, let's say you want to know if it's going to rain tomorrow or not, then you collect so many factors like humidity, wind, and so on and so forth. So you now looked at all those chances. When it's greater than a particular threshold or not, then it's going to rain. If not, then it's not going to rain. So the same way it's been done here. So if it's sunny, it means that what is now going to be the humidity. So when you looked at the humidity, is it less than or greater than, is it less than or equal to 75? If it's yes, then the chances that it's going to be to be raining is going to be small. And then if it's greater, then if it's greater than 75, which is a no, then we choose the other outcome. Then the same thing again, you moved to this side. So if it's rainy, it's going to be a different thing entirely. It brings us to, is it going to be windy? So the first thing is, after you come to the roots, you have the splitting, then the decision node. So the decision node will determine what the outcome becomes. Then when you have this overcast, so now the next thing is wind. Is it going to be windy? If no, then you have your decision. If yes, then you have your decision. And if you are a good student of geography, most of the time when there is wind, you don't really have rain. You see, the rain will just go. I remember growing those days in Idoma land. We say it went with the wind, something like that in Idoma. You know, they say the rain didn't fall, it went with the wind. So the same way, you know, you could see. So the tendency that it will rain it will rely on some of these factors. So there is another thing I want to talk about is the maximum depth of the tree. So this tree, for example, this one is just like three depth. But if you increase the depth, so the depthness will be how, so what you do is you could trim the tree, or you could continue to increase the depthness. So you could go to 1, go to 2, go to 3, go to, like that. So the depth could be 4 depth, it could be 5 depth, it could even be n depth, but you have to be careful because the more you go down, the more bigger the tree becomes. So just like the normal tree that you have, when you have a normal tree, you start with the branches, then the branches will begin to stretch out to form other sub branches and subsequent leaves. So the same way with the decision tree, it starts with the root, then it splits, then it moves to the decision node, and so on and so forth. So you have to make sure that whatever you're doing, you're kind of careful with it. So that talks about the major algorithms we have in the regression problem. So talking about classification problem, remember we talked about classification problem has to do with categories, okay? So however, in the simplest in the classification problem, most of the time is the logistic regression, and there is this argument sometimes good about if the logistic regression should be considered a statistics issue or it should be a machine learning stuff. But these are not really important. However, in the case of the logistic regression, we discovered that it's not always true that the regression has to be continuous. There are situations where you now have a binary case, but it seems to look like a regression problem. So what do you do? Do you now go to use the regression approach to approximate it, considering the fact that these outcome variables are not continuous? So when you do that with a regression, you will not get anything because the outcomes are not continuous. So if you draw a straight line here, you are likely going to miss out what is happening in between. So they now came up with a sort of like a sort of like a sigmoid function kind of transformation to help us to be able to capture these problems, but in form of ratios or in form of probabilities or ranges. So it means that we begin to look at where does this y lies. Is it going to be, it will lies within 0 and 1, but now we will be much confident if it tilted towards 1, and maybe we'll be less confident if it tilted towards 0. So the reason is because you now have this outcome happening here, and you now have this outcomes, the variables happening here. So you cannot specifically omit what happened in between. So those are some of the arguments of what we come. So this is more like a sigmoid function. And last time we talked about how this was derived with John, and I wouldn't go that in detail. So there is another most common algorithm called the support vector machine. So the support vector machine came into being, and I think I used this during my master's for my master project. I used the support vector machine. It's quite a very interesting one. So the support vector machine is using the concept of what we call the hyperplane, and then it's sort of divide these variabilities. And then from the hyperplane, you looked at the distance between the margins. And the margins could be hard margin and it could be soft margin. So those ones that are very close to the margins, we call them the support vectors. So the closer to them, the better. So sometimes we could have an overlap. And then that takes us to the concept of kernels. So what happened in support vector is that you take the futures, project them using the kernel into a plane. So for example, when you're having very complex features, the linear regression, logistic regression, all these simple models are not likely going to do well because they always come with a linear thinking. So the support vector, on the other hand, tells us that no, if we use some sort of transformation called the kernel, we will be able to take those features, project them into a higher dimensional plane, and then we could, in those high dimensional plane, think of them as if we are working in the XY plane. So from there, we would be able to approximate this problem more efficiently. So that's what it's trying to understand using this support vectors, the margin and the hyperplane concept. And this has a different mathematical derivations where you maximize and minimize the margins and the hyperplanes. And I wouldn't want us to go into this because that's quite more for mathematicians and statisticians. But anyway, so we also have the random forest. Now, and again, if you take note very clearly, you will see that the random forest looks like the decision tree we talk about. And you are right if you think that way, because the random forest is a bunch of decision trees that were combined to build on the concept of majority voting. So the random forest will take the what happened from decision tree 1, from decision tree 2, down to decision tree n, and then it will now look at the majority. So just like democracy. So the random forest is some of the democratized decision trees coming together. So it looks like the case of Nigeria, for example. Anyway, Nigeria is not really practicing democracy, but we would just on paper say that, yeah. Anyway, let's not go into that argument. So let's look at a country like US. I think that's more better to talk about democracy from that angle, compared to Nigerian issue. So, looking at a country like US, the president doesn't just come from one particular vote from one block. It has to pull all the blocks, and then by the time it pulls those blocks, when he has the majority, then he emerges as the winner of the election. I followed the last election in US, and I could see that Donald Trump had to win several states, key states that were formerly Democrat states. He has to win those states, in order for him to be ahead of Kamala Harris. So the same way, the random forest works. So you take one region. So let's say this region, you take the vote from that region, you take the vote from another region, take the vote from another region, then you now aggregate them. When you aggregate them, the majority vote will now take the lead. So like in the case, you look at different you look at the different for example classes. So if we are dealing with a binary problem, and then decision tree A vote that the outcome is 1. Decision tree 2 votes that the outcome is 1. And decision tree 3 now votes that the outcome is 0. You see, we now have 2 against 1.
Yes.
Good. So that's what it's been about. So by the time we have 2 against 1, we are likely going to say this outcome is 1 because 2 of the decision trees said it is 1. So that's how the decision tree works. Then we have the k-nearest neighbor.
Doctor, can you explain this random forest simplified? This decision tree, can you explain it again? I'm trying to decode it.
Okay, no problem. So, like I said,
explanation.
So, like I said, remember we talked about the decision tree, the single decision tree, when I was talking about regression problem. That it has a root, it has the splitting, it has the nodes, the decision nodes. So the same way that we have one single decision tree, the random forest is the combination of so many of the decision trees. So you can combine up to 1,000 of them. You can combine up to even 100,000, depend on what you want. So you can combine, let's say, 10 of the decision trees. So by the time you combine these 10 of the decision trees, the way they will arrive at determining the outcome is by majority voting. So decision tree 1 is going to vote based on, remember, we are feeding the futures into the algorithms. So when we feed the futures into the algorithm, it will process them during training. And remember, we will give the future, during training, we will give it the label, we'll give it the futures. Then we are going to tell it to come up with, we are now teaching the machine to know the futures of each of the outcome variables, to know what patterns can determine if this outcome is going to be a cat, if this outcome is going to be a dog, if this outcome is going to be a zebra, for example. So the same way, if we have several of the decision trees combined, let's say decision tree 1 said it is a cancer. Decision tree 2 said it is a cancer. Decision tree N said it is not a cancer. Now you have 2 against 1. So because you have 2 against 1, you will vote to be what? To be 1.
Yes.
Because 2 people have agreed it is 1. So just like there in election, not everybody would agree with your candidate, but the candidate that have majority votes emerges as the winner. So the
Yes.
same way we are doing in the case of random forest. Not all the decision trees will arrive and said this is it, but we will only make output what the majority agrees upon. So if the majority of the trees agree that the outcome is 0, then we will output 0. If the majority of the trees agree that the outcome is 1, then we will output 1. Okay, so that's
Yes.
what the random forest is all about.
Thank you,
Then,
sir.
no problem. So the case of k nearest neighbor. Now, if you remember, I told you in a previous video about briefly on the k nearest neighbor, where I told you it said the k nearest neighbor, it's going to also use the concept of averaging. But in the case of the averaging, still like a case of voting. It's kind of also voting, because what it's going to do in the case here is that it will look at the neighborhood before it's going to arrive. So the tendency that the new instance is going to belong to one of the classes is going to be based on the proximity of its neighborhood to that particular instance. So if we have a new outcome, we would look at the way this outcome is being distributed, which are the people closest to it. For example, if you are taking k nearest neighbor 3, means that you are going to look at the neighborhood of 3. So it means you are going to consider 3 at a time. So let's say 1, 2, 3, and then you decide what this new outcome here becomes.
Okay.
Then if you are having 7 neighborhood, you increase the radar. You increase it again. So this will be 1, 2, 3, 4, 5, 6, 7. So this is 4 of them, and this is 3. So you expand. Then if you are taking 11, for example, you increase this radar to cover more bigger picture. Like that. You continue to shift the bar. So let's say in the case of k nearest neighbor is equal, this is equal to 3. And you want to determine what this outcome here is going to be. If you look at, in this case, 2 of them are green, 1 of them is red. So you
Yes.
will likely say this is going to be a triangle.
Okay.
You see the thing? So,
Yes.
but when you are saying it is 7, it means you are covering more grounds. So now you are going to now vote now and say 1, 2, 3. So 3 of them said it is green.
Triangle.
Yes. Yeah. Then 1, 2, 3, 4. But 4 of them said it is red. So it means it is likely going to go for red. Do you understand the concept?
Yes.
So what
Yes.
it does is it will look at the neighborhood and then it arrives at the decision. So each of them have a unique way of understanding the problem. So in the case of random forest, the fact that we combine these decision trees, we call them assemble methods. So assemble because
Okay.
we combine several decision trees to become one. Nigeria is a good example of an assemble classifier. You combine Hausa, Igbo, Yoruba, then you now begin to have other tribes, Idoma, Efik, Calabar, different these things together. So it's an example of an assemble method. You assemble them, but in the case of random forest, they all have a unique pattern. They have a unique this thing. They were all decision trees. So they are similar. They are similar in nature. So because they are similar in nature, most of the time we say these are bagging. Is a bagging approach. Okay, so the assemble method here is a bagging assemble kind of method. But when we have different classifiers, for example, because I want to leverage on the power of each of these algorithms, because you can see all of them have a unique way at which they are approaching the problem. Support vector will use hyperplane, margin, and support vectors. Logistic regression will look at the curvatures that happens, the sigmoid function helping us here. And then random forest aggregates the decision trees. K-nearest neighbor bring all consider the neighborhood before. So some people will argue that instead of using one algorithm to make decision, why don't you combine all the algorithms together? That if you combine them together,
accuracy of the
exactly,
results.
yes, you are likely going to be confident of the decision that you are going to get. So such kind of people approaches will suggest that combine logistic regression, support vector, random forest, and also k-nearest neighbor. Aggregate them together, and then you form an assemble classifier. And then you can be able to make decision based on that. And that was what I did during my PhD. I combined all these traditional classifiers, and then I came up with an assemble classifier, and then I arrived at my final classifier for my problem. However, the problem here is complexity. The more you combine these classifiers, the more complex they become, and the more computational demands they will require from you. So sometimes you have to weigh in. Do you have the resources? And when we talk about the resources here, we talk about the computational efficiency. Do you have the computational efficiency to be able to combine them? Do you know also the time? Because when you combine them, the training and the prediction time are likely going to increase. So sometimes you have to put all these things into consideration. Do you really need a complex model, or you just need a simple model? But the thing is this, you must have a reason why you use something. Don't just use it because it looks exciting. Rather, be convinced that what you are using, or justify that approach before you use it. So that way you will be able to be happy that what you're doing is something you understand and is something you can be able to explain to anyone. So don't just rush to use an algorithm because you want to know. Rather, I would suggest you explore all these algorithms and select the best one from them. Then if you must use the complex model is when all these ones fails, and you notice that each of them have an advantage that the other one does not have, then you could be able to combine them together, and then you could be able to leverage on the advantage of all of them and be able to make a more, like they said, two heads are better than one. So two good heads, don't forget, are better than one, not just two heads, because two heads can still be there
It's
and they will
true.
not be
It's
better
true.
than one. So it's two good heads. So if you leverage on them, you could be able to be much more powerful. You could be able to get more this thing. So, but you have to justify the reason why you want to combine several of these resources together. So those are the common traditional approaches we have. So quickly, we would be going into the hand-on. I actually discovered that our 1 hour time has sorry. I noticed our 1 hour time has moved.
Yeah.
And I wanted to take the practical section. Anyway, let's see what happened. So the demo section, we wanted to go into Jupyter Notebook to be able to do that. So let's quickly go into that. Let's skip. So for you to do that, all what you need to do again. So let me start afresh. So for you to do that, you need to open your CMD, or click on that. It's going to come up. So the CMD, it allows you to be able to interact with the computer directly from the shell. However, sometimes when you write the script, you could run into errors. So that's why the Jupyter Notebook will help you, especially for novice, to be able to be writing your code and be interacting with them one after the other. So that's why it's very important. So to open the Jupyter Notebook, you type in Jupyter Notebook on the command prompt. So once you do that, it's going to pop in, and then it's going to open the Jupyter Notebook. For you to do that, you must have installed it before now. So make sure you have installed the command prompt, the Jupyter Notebook before doing that. So once we are on the Jupyter Notebook, I have already have the script before now. I did that yesterday. So I will quickly navigate to where the script is. So I think it should be examples. Yeah. Examples, I think regression examples, if I'm not mistaken. Yeah. So regression classification. So this is the practical section of the slide. So you're going to open this. So John, I'm going to give you guys this script after the class. Okay, but anyway, I can send you the script now, so you can also run it from your end. Are you with me?
Yes.
Okay,
I'm
good.
here.
Okay, good. So let me give you the script. Okay, so I've sent it to the group. You'll be able to download it from there.
I think. Let's check.
Or do you want me to send it to your email?
I think I should be able to download it from.
Okay, fine. Great. That's a good one. Okay, so quickly, if you're able to download it, you can proceed.
It's still loading.
You have downloaded.
Yes, it's still downloading.
Okay, great, fine. So, okay, so it is the first one is going. The first data set we're looking at is on a regression problem called the Boston housing data set. It's a classical data set that is used in regression analysis and machine learning. It contains information about housing prices in suburbs of Boston collected in 1970. Although this data set had issues on Scikit-Learn, so they pulled it down because of a racial concern, so they kind of not okay with it. So take note of that, okay? Anyway, so the data set contain these features. The first one is prime, that's per capita crime rate by the town. ZN, proportion of residential land zone for large lots. Then Indus, proportion of non-retail business acres per town. Then there is the Charles River dummy variable, NOx, nitric oxide concentration per 10 million. Then RM, average number of rooms per dwelling. Then age, which is the proportion of the owners occupied units prior to 1940. Then we also have the DIS, which is the weighted distance to 5 Boston employment centers, RAD, and so on and so forth. We also have the tax and other ones. So there is the median value of owners occupy home. So that is the target variable that we are interested in. Okay. So in order for us to start working on the data set, we need to load the right Python packages. So you must have installed this package using the pep install. So you must have come to your command prompts. Before you do that, you must have installed your Python. So once you do that, you could install with pep install pandas, and then you go. Then you do the same for NumPy, pep install NumPy, you run. And once that is done, then you also install Scikit-Learn, pep install, I think Scikit-Learn, if I'm not mistaken.
Okay.
Scikit-Learn or Skit-Learn. I think it's Skit-Learn or so. No, let me get the right. I'm always calling it Scikit-Learn, so I'm kind of used to it. Yeah, so the right word is Skit-Learn here. You could copy that.
I think I already installed that day.
Yeah, so Skit-Learn, Skit, then hyphen learn. Then once you have installed that, the next one will be Matplotlib. Okay, pep install Matplotlib.
That one I don't have.
Okay, so I already have them, so I don't need to install. Then
Pep
the next
install.
one, you pep install Seaborn. Seaborn. Yeah, Seaborn. That's C with born. Seaborn.
Enter.
Good. Okay, so that with that done, you can now run the first cell. So you just load. So what we are doing, we're importing the right package. So once you have done that, you need to load the dataset. So this dataset, we download the dataset from GitHub. So you can find it on this link in GitHub. So for you to read the dataset, you need to use pd.readcsv, then the data URL. So once you run this, it's going to read in this dataset from this link, and then you can be able to see. So to see a preview of the data, a preview of the data is df.head. Then you run. So once you run this as well, so this is going to show us the data. So this is a brief about the data. So we talk about all these features. So you can see all the features, and then you can see down to the dependent variables here. So the next thing we need to do is we need to understand the data set. So we have read the data set, but we have not yet know what this data set is made of. Of course, we have seen the view of the data set, which makes sense, but we need to also know much about the data. So we could see the shape of the data set. It has 506 rows, and it has 14 variables. So the first one here is the rows, and the second one is the variables or the columns. So this is the rows, this is the column. Then the column name, the 14 column names are listed here, and they are all objects. Then we now interact to know the data type. Remember from the beginning of this class, I told you about different data types. If it's a float, an integer, and if it's going to be what do we call the other data type? Objects and all that. Yeah. So the same thing. So you can see all the data here shows that they are all floats. Okay.
Then integer.
Sorry, yeah, they are all okay, sorry,
Have
radar
three
and
integers.
tax are integers. Yeah,
Yes.
so there are 3 integers and
The
all. So the
cast.
next exactly. So the next thing is you check for missing value, because this will also check if it calculates the number of missing values. So this is important, because if you have missing values, you may have issues running the model. But not all models, like decision tree models, could handle missing information, but it's good you check. Okay, so you could see actually in this data set there are no missing values. But the real world will not be like this. The real world, you likely going to see missing values coming up. So the next thing is you run the descriptive statistics by using the f.described. So this will give you all the descriptive statistics, like the mean, the standard deviation, the minimum, and then the 25% percentile, the 50%, which is also the same as the median, and then the 75% and the maximum. So here it will give you a rough idea about how the data is distributed, and you could be able to understand what the data is saying. So the next thing you need to do, we call it exploratory data analysis. So what you need to do is to visualize the data by making plots. So you could be able to understand how this data is visually represented, okay? You don't just start modeling your data set. No, interact with the data set, know the characteristics of the data set, visualize the data set, and then you could proceed to the modeling part of the data set. So the next thing you need to do is to run a regression on the data set. So no, sorry, histogram. Okay. Now the reason we're using histogram is because these are all continuous value, although we do have integers, but they are more continuous. So you could see for cream, most of them are skewed to the left. Zine, we have a lot of them concentrated around 0. Indus, we have also skewed to the left, and a bit of high ones. Age, skewed to the right. Most of it is moved towards older population. From 50, it's tend to increase. The tax is kind of normally distributed, rather not. Easter is also skewed to the left, kind of. And then the medic, which is our target variable, it's kind of, not really, but it's heavily concentrated around 20, and then it started decreasing drastically. So we kind of have an idea of how the data virtually is represented. We can go ahead to look out for outliers. So a very good plot that you could use to check for the presence of outliers is the box plot. The box plot helps you to be able to detect if outliers. So what the box plot does is that the box plot will look at the maximum, the minimum, and also the median value. And then anything outside this range are considered outliers. But it depends. Again, if your study is not really concerned with outliers, then you don't have any reason to be worried about removing them. So you could see almost all the data set did have outliers outside tax. Tax, like I said, it was kind of normally distributed. For most of the data, you could see for cream, most of them have upper sort of outliers, then Z to have, and then B here did have lots of outliers as well, but it was on the lower values compared to, it doesn't have anyone on the upper values. So that's good. At least you could see and understand how distributed your data are. So like I said, these ones are like the median sort of value, and then these ones are like the area within the standard deviation, so the max mean sort of things. Then you be able to run also the scattered plot. So for example, so we want to understand the relationship that exists between Easter and the target variable. So remember the target variable in this case it's just a scattered plot. So the Easter is on the y-axis, is on the x-axis, and the median value, which is the median, is on the y-axis because it's the target variable. So normally try to put the target variable on the y-axis because it goes up or come down depending on how the x-axis moves. So you could see how distributed this is. So the next thing we need to do is to perform some sort of association test to see how this, and then also visualize it. So it's not just to perform the correlation, but we visualize it. And this correlation here is just a simple Pearson correlation, not the Spearman. ranking, but they both wouldn't be different. But anytime you want to, the difference is that Pearson correlation is not too sensitive.